Um, Hope we're feeling okay. And just wanted to take the rest of our time this evening to go over the lab assignment that will be due next week. Okay. So there are two parts to this lab. Each part is worth 10 points. Um, these labs come from a free online textbook called Open Intro, which is quite good in of itself. You can read Open Intro Statistics, and you can read the textbook. Hey, the textbook that we are using for this class is also very good, and I'm happy to use it. But you know, should you sell that or you know give it away or whatever, and you find yourself in need of some kind of statistics reference material, I do recommend this Open Intro textbook as well. It's a free resource. You can download the PDF. But anyway, we have two labs here, and they are well, in their textbook it's 4A and 4B. I don't assign as many labs, so this is just our lab 2A and 2B. Okay, and so if you open up the file, it starts off here, and you're just gonna kind of read through it and follow the instructions here. Okay. Be sure to read the text as it explains what you're doing, and not just jump to the code and start clicking things around. Okay. So what we're doing in this lab is that we are looking at some real estate data from the city of Ames, Iowa. Okay, and it contains every real estate transaction that was recorded in the city assessor's office, and we're going to look at residential home sales between 2006 and 2010. And so to get this data into R, we are going to use this command called download file. Okay, and what it does is it downloads this file and it stores it in the destination file ames.rdata, and then we're going to use load ames.rdata. Now, you can try to highlight and copy and paste into R, but that doesn't always work because you're dealing with a PDF, and sometimes the PDF has like these hidden characters, or it puts spaces in weird spots, or little line breaks or things like that. So kind of the foolproof method would be to type the command exactly as you see it, okay, into RStudio and to run it. Now, let me just explain something. I think when you start RStudio, here I'll exit here, and I'm going to fire up RStudio. When you start it up, I think it looks something like this. Okay, and what I recommend is you create a new file, RScript. Okay, and when you create a new script, it opens up this page up here. Okay, and this is where you can type your commands. So in this case, I'm going to write download.file quote http:// okay, and you want to make sure your text, the lines that you are writing are exactly the same as they appear in the in the lab here. Okay, and so you type this out, and this is just basically a text editor, and so typing things over here does absolutely nothing. Okay, you're just typing text. However, it's linked with R And so you can, on each line, you can hit Control Enter, or if you're on a Mac, Command Enter. And what that does is it takes whatever line your current cursor is on, and it throws it into the console as if you typed it down here. So while my cursor is up here, I'm gonna hit Control Enter because I'm on a PC. But if you're on Mac, you're gonna hit Command Enter. And what it does it throws it down there, and right here it says error, could not find function, download file. Okay, and that's because I misspelled it. And so the nice thing about having the working in the editor up here is if you've made a mistake, you type something in wrong, you don't have to retype the entire thing. You can just go back and say, oh, I left off the letter O here, okay, and then you hit Control Enter, and that time it worked. And it says trying URL, and it says downloaded. Here you go. Okay, and then when you do that, it automatically moves the cursor down to the next line. So you can just hit Control Enter again, and now it has loaded the data. And we can see that it worked because suddenly I have stuff over here. I've got this aims data as well as two functions that it has created. Okay. And again, so you can try copying and pasting it. I'll try that with this stuff right here, and I'm going to try copying and pasting it into here, and it appears to have transferred correctly, but there is a possibility that it didn't work out, and in that case I'm going to have to retype it by hand. Okay, so I just want to explain what this thing does is that if I click this data over here, it's going to open it up kind of like an Excel spreadsheet, and we can see it says 2,930 observations of 82 variables. So there's going to be 82 columns and 2,930 rows, which is a lot. And it has things like the property ID, subclass, the zoning, whatever, the frontage, lot area, street, all of this information. And the only thing that we are interested in is the living area of the house, which is given by the column grlive.area, okay, and the sale price over here, which is in dollars. Look at these houses, $215,000 for a 1,600 square foot house. You just have to live in Iowa, but not a bad place to live. But in Los Angeles, we don't see prices like this. Okay, so anyway, we can reference that column of data by using the $ notation. What this says is look at, and I think you're already kind of familiar with this from the blood pressure data, is we're saying look at the data set, or it's called a data frame, aims, and within that the $ says look at the column called gr.live.area. And over here look at the data frame aims, and within that the column sale price. And what we're doing is we're taking the output here and storing it into area. So I'm going to just hit Control Enter, and it runs that, and we can see we've created a new set of values here called area, and I hit Control Enter here, and we can see it has created a thing of price. And this looks right because it says 2,930, which means there are 2,930 entries for area and 2,930 entries for price, which is exactly what we would hope to see. Okay, so as we're looking at this, it says, look at the summary and create a histogram of area. So we can just do summary of area and histogram of area. Okay, so if we do summary, it says the minimum 334, that's the smallest house, and then the biggest house had 5,600 square feet. And if we look at the histogram of area, how would we describe this shape here? Right skewed, right? So most houses are kind of in this 1,000 to 2,000 square foot, but we do have a few houses that are very big. Okay, probably, you don't have to do this, but if you wanted to, you can do increase the size number of breaks. Breaks equals 25. I think you saw something like that. So this kind of shows more clearly the skewed nature of our house areas. Okay. Okay, so it says describe this population distribution, and it looks like that. And what we're going to do is we're now going to start drawing samples from area. So keep in mind, area is just, it's a list of 2,930 values. Okay, so we can think of area, this thing called area, as 2,900, a list of 2,930 numbers, each of them corresponding to the size of a house. And what we're going to do is we're going to draw a sample from area, and we're going to take a sample of size 50, okay? And we're going to store the results of that sample into samp1. Okay, so I'm going to call samp1, and all this is going to do is it's going to take that list of 2,930 numbers, randomly select 50 of them, and it's going to store those 50 selected numbers into samp1. So it's done that. So samp1 we can see has 50 numbers in it, and we can look at all 50 numbers in samp1. These are the 50 numbers, the random numbers that it drew, which it's hard to really say anything when you just see the raw numbers. Okay. And it says, things like describe the distribution of the sample. How does it compare to the distribution of the population? So right now, when you just look at the sample, you can't tell anything, but you can ask for the same kind of functions that we applied to the population, which would be area, all 2,930 numbers. Here we can just say, let's look at the summary of the 50 numbers we drew. Okay, and so we see that the mean and the median are, in the ballpark. The max isn't as high, but the first, second, and third quartiles are all kind of in the same ballpark. If we do a histogram of samp1, oops, you have to hit Control Enter. Okay, this is what we see, which may not be very telling. Let's increase the number of breaks and see if that does anything. Okay, and so this is what we see with a lot of breaks. Keep in mind the axis across the bottom, and how does this compare versus the population, all 2,930. So the labs says exercise 2. Describe the distribution of the sample. Oh, so actually, I should take a moment and say, for the first lab, I didn't dock any points if you turned in labs that were kind of like screenshots of your R code or something. But for this lab, I don't want you to just print, copy and paste the stuff that you see in R. Okay. What I want you to do is, fire up a word processing document or program of some kind, and as if treat this as if you're turning it in, because you are, and you're going to at least write lab 2A and exercise 1. So exercise 1 says describe this population distribution. So you don't have to copy the question prompt, but so you can say the population is unimodal and right skewed. It has a mean of, and going to R, you would look at this. It has a mean of 1,500 and a median of 1,442. Most, etc., etc., etc. Okay, so you would answer answer these things, and then if you want, you can then insert. You can copy and paste code into your document as kind of like supporting documentation of your claims here. Okay, so you know, and if you wanted to include the histogram, so a nice thing about RStudio is there's these little back and forth arrows. So as you produce more plots, you can always call back some of the earlier plots that you created using the back and forth arrows here. So if you got something like this and you want to put that in your Word document, you just click export and you can do copy to clipboard, okay, and then it says you can kind of change how big you want the thing to be. So if you want this, you just click copy plot, you come back over to Word, and then you hit paste, and it goes right into Word. So it's very easy to add kind of supporting plots or output into your document. Okay, there's actually another system called R Markdown, which is an entire lecture in of itself that kind of updates all the plots on the fly, and it's really neat. But I think this method is also just as good too. Okay, but so anyway, for this lab, please put it into some kind of Word document or something, and then answer the appropriate questions and exercises as you would with a thing, and then include the supporting documentation or diagrams as necessary. Okay, so going back to the lab, it has you do this, and so it says describe the distribution of the sample, and you can call on things like mean of the sample and things like that. After you and then for exercise 3, it says draw another sample and describe that. Okay, and here we're going to build up a sampling distribution here. Okay, and what we are doing is first we're creating a place to store all of our results. Okay, and that's going to be sample means 50, and what this command says is repeat the number 0 5,000 times. Okay, so we're going to create this, and then we have to run it. So copying it into here doesn't run it. You have to hit Control Enter, or you can also click this button that says Run, and that it's the same thing as hitting Control Enter. It takes the current line that you're on and it throws it into the console. So here is 5,000 zeros, and then we're going to run this loop here. Okay, and what this says is for I in 1 through 5,000. Okay, and basically that just means I starts off at 1, and then it runs through the commands inside these curly braces, and then once it finishes that, I then bumps up to 2, runs through the same commands again. I bumps up to 3, all the way up until I reaches 5,000. Okay, and so the computer doesn't mind doing these repetitive tasks over and over, whereas if you were to ask a human to do this, they would get upset with you. And so here, every time it runs through, starting at 1 all the way up to 5,000, what it does is it takes a sample of 50 numbers from the population area. Again, area contains 2,930 numbers. We're taking a sample of 50 numbers, and we're temporarily storing that in this thing called SAMP. Okay? And then we find the mean of that sample of 50 numbers. So keep in mind that SAMP here are these 50 numbers that we drew. We're going to find the mean of those 50 numbers. And then we store the mean of those 50 numbers into sample means 50 bracket I, which means currently sample means 50 is 5,000 zeros, but when it runs through it one time, the first time when I is 1, it replaces that first 0 with the mean of the first sample that it took. Then when it runs through the loop again, it draws a new sample of 50, takes the mean of that new sample, and then it updates the second number, and sample means 50. Okay, and it keeps doing that, updating every single number from 0 into the sample mean until it reaches the end 5,000. Okay, so I can say run this code. So I highlight this and I can click run or control enter, command enter. Okay, and we can see that sample means is no longer a bunch of zeros, it's now a bunch of numbers around 1500 something. Okay, so we've taken the means here. Okay, and so this gives us an idea of the sampling distribution. So remember, the sampling distribution is the distribution of those sample means. Okay, and you know, the sampling distribution is technically the distribution of all possible samples, or all possible. I'm sorry, is the distribution of all of the sample means from all possible samples. Of course, we're not going to draw every single possible sample, but by doing this process of random sampling 5,000 times, we get an idea of what all of the different possible samples might be. Okay. Okay, and then now that we have done that, we can describe the sampling distribution, and I'm just going to go ahead and jump to the version with breaks equal 25. Okay, so we're going to create a histogram of the sample means. Sample means 50, meaning we're taking the sample means when our sample size was 50. Okay, and here we have it. Okay, and so this looks a lot like what? A lot like the normal distribution. Okay, and so you can use this to answer questions from exercise 4 or whatever it might be. Okay, how many elements are there in sample underscore means 50? What is the answer there? How many elements are in sample means 50? How many sample means do we calculate? How many times did I run through the loop?
5,000.
Yeah, I ran through the loop 5,000 times. Okay, every time I ran through that loop, I drew a sample of 50. Okay, I drew a sample of 50 and I calculated its mean. But how many elements are in here? There's 5,000 because I ran through the loop 5,000 times. And then the question asks, what would happen if instead of 5,000 I ran through the loop 50,000 times? What would happen? How would that affect this? What do you think? Yeah, I would say it probably would not affect this anymore. Okay, it would probably look almost exactly the same here. Here we might notice just a little bit of like it's not super smooth. Okay, but I think I could do this right here very quickly. So running through this. So is there much difference between this one and this one? This is the one with 50,000 and this is the one with 5,000. They look very similar, okay? And, we notice in terms of the scaling down at the bottom, it doesn't change very much, okay? After doing it 50,000 times, it seems like we got one or two really extreme samples, whereas with 5,000, the most extreme one was, down here, whereas with 50,000, we did get one that was maybe slightly more extreme. And in terms of but the shape, they both look very normal. It's just maybe with after 50,000, it looks more smooth. But in terms of pointiness, or is it now no longer skewed or whatever, I would say with 5,000 or 50,000, it didn't really seem to affect it too much. Okay. So keep that in mind. So I'm kind of giving you the answers for at least the exercises here, okay? And of course, I'm recording this so you can watch this video to help you through it. Okay. The code here does what, or not the code. The lab enters an interlude explaining the for loop, saying we're doing this over and over and over again. And you can read that, and that might be good to read. So anyway, we can further do this, and rather than taking samples of size 50, we can take samples of size 10 and samples of size 100 and see how that affects our the sampling distribution here. Okay, so basically so what will happen, how do you think the sampling distribution will look for sample means 10 and sample means 100? Okay, well, how so? What do you mean? So here I'm going to create sample means histogram for sample means 10 and sample means 100. Basically, every single time I'm just running through the loop, and I'm taking a sample. For sample means 10, I'm taking a sample of 10 numbers from that list of 2,930, and then for sample means 100, I'm taking 100 numbers. And each time I'm just taking the mean of those samples. So what do you think?
The 10 wouldn't be more skewed. It's a smaller number.
Yeah. So here I'll show you. Okay. So this is what it looks like with 10. So we do have a little bit of skew. Okay. And notice the spread. We're going from around 1,000 to around 2,000. Seems to contain pretty much all of the numbers here. And with 100, what do we have here? Almost all the numbers are between 1,400 and 1,600. Okay, and then this is sample means 50. Almost all our numbers are between 13 and 1,700. Okay, and this is maybe 1,350, 1,650, something around there. Okay, so these are after sample mean 50, sample mean 10, sample mean 100. The difference between these samples is the size of the samples that we're drawing here. Right? And that affects, if you think back to our sampling distribution and the central limit theorem, how does the size of the sample affect the sampling distribution?
Less error or standard error?
Yeah, the standard error shrinks for those things. Yeah. Okay. So you can do that, and then you're responsible for answering these on your own questions. Okay, so that's the first lab. You're going to answer the exercises as part of the lab, and then the questions in the on your own section. Okay. I think the lab is not intended to be crazy hard, but I think sometimes people just make small little mistakes. They capitalize something, or leave put a space in the name, or something like that can cause frustration. I can tell you that the code here works perfectly fine. So if you're encountering errors, then probably you are typing something wrong, or something is not exactly the same as it appears in the code here. Okay. Okay, so let me talk about lab 4B then. So this is the second part of the lab. Okay, or the second part. This part, then we are going to generate a whole bunch of confidence intervals. Okay. Now, what I recommend is after you complete the first lab, I recommend clearing your workspace here. Okay. Just because after the first lab, you're going to have a whole bunch of kind of junk inside your inside the computer workspace. So I recommend hitting this this broom here. Okay, this little broom under Environment. So you've got the History tab and you got the Environment. So under Environment, click the little broom, and it's going to say, "Are you sure you want to remove all the objects from the environment?" And you just click Yes. Okay, and so now it's all empty. Everything is gone. Okay, and then you can choose to start a new R script, or you can continue on here. But you're going to have to, reload the data. So I'm going to try copying this as it appears here, and we'll see if that works. It looks like it might actually work. Oh, look at that, it did. Okay, so sometimes copy and paste works, sometimes copy and paste does not work. So your mileage may vary, okay, regarding that. And then we say load this data. So this is a common mistake people do, is they try to click this address and like try to download this file or something, don't do that, okay? Don't try to go navigate. Don't try to navigate to that to this page, okay? What you got to do is you got to type this command into R as it is, because this will tell R to download the file and load it into R. Okay, because if you try to download it and then open it like this, actually my computer's set up so it works, but your computer's probably not set up, and you're going to see all of this gibberish text and things like that. So so don't do that. Okay, make sure you type it in. All right, and so in this case, we're doing some very similar things. We're drawing samples from the population. Here we renamed the area into population, but population here is exactly the same as what we had area earlier. It's a list of 2,930 numbers, and it's the square footage of the home. So we had 2,930 homes sold in Ames, Iowa in that time period, and we're listing off the square footage of every single house that was sold. So here's a list of all 2,930 homes, and we're calling that the population. Okay, and what we're going to do is we're going to draw random samples from this population. So here we're drawing a random sample of 60 numbers. Okay, and then what we're doing is we're going to calculate the mean of that sample, and then we're going to create a confidence interval. Okay, now this is I want to explain this. In this lab, they are using the numbers 1.96 as the kind of the number to use for the confidence interval. So students always ask me this. It is not correct to use 1.96. Okay, it would be more. What they should be using is the value from the t-table that corresponds to 59 degrees of freedom, because we have a sample of size 60. Okay, so you have a sample of size 60, we should have 59 degrees of freedom, and we should be using the t star that corresponds to it. Okay, this value 1.96 is actually what we would be using from the normal distribution. I think they're kind of in this lab, I don't know, maybe they didn't teach the t-distribution or whatnot, so the true number is probably something, it's a little bit bigger than 1.96, and R actually has a built-in t-table, and we would just do a qt for 50.975 with 59 degrees of freedom. So instead of 1.96, the true value is 2.000995. So almost 2 exactly. But for whatever reason, the lab chose to use 1.96. You can continue using 1.96 if you want to update it to say 2.000, whatever is in your T table, okay? Using either 60, in the table you can use 50 or 60 degrees of freedom. You're all going to kind of get in the same ballpark number. We're just changing things by, at most, a 2% difference or something. It's okay. Alright, and so basically what we're doing is we're calculating the standard error. The standard error is the standard deviation of the sample divided by the square root of n, right? So the standard deviation is calculated using the function SD, and then the square root is we're just doing square root of 60. So this is our formula for standard error. Okay. And they are calculating the lower and upper bounds of the confidence interval, doing the sample mean minus, this is basically, you can think of this as T star times the standard error, sample mean plus T star times the standard error. They're using 1.96, which is not technically correct, but for the purposes of this lab, it's kind of close enough, okay? So they are calculating the lower bound, and then anytime you see this dash, this means store it into this thing lower, and then store it into this thing upper. Okay, so we can do this, and what this command does with the C says, combine these two numbers into one output. And so it combined the lower and the upper into 1404 and 1648. Okay, and so here is our confidence interval that we have. And if I wanted to, I can call this T star. It says T star. So I've got T star, and so T star is actually 2.00995. If I wanted to use T star here instead of 1.96, I could. Okay. I will not, whatever you decide to do, I will not dock you either way. Okay. So, using 1.96 versus using T star, you can see the change it has. It changes it from a lower bound of 1404 to 1648. Using the T star from the built-in table, we can see it gives ourselves just a little bit more cushion to 1401 and 1650. So we're just giving ourselves a little extra padding in our confidence interval. But it makes a very small difference. Okay, and then so you have some questions about all of this stuff. But what we do then is we calculate, we're going to do, repeat this 50 times, okay? And so we're going to run a loop, and every time we run the loop, we're going to draw a sample from the population. In this case, we're drawing samples of size 60. Okay. And then we run the loop 50 times. Okay, so we're going to draw 50 samples of size 60, and every time I draw a sample, I'm going to calculate its mean and its standard deviation. And all of these are stored in sample mean and sample standard deviation. Okay? And then at the end of this, what we can then do is we can create 50 confidence intervals. Alright, so we can repeat the process of creating confidence intervals 50 times, and we can see kind of how our confidence intervals compare with one another. Okay, so I'm going to just run this. So it's already done. Okay. So here I've drawn 50 samples of size 60, and I've stored all of those results in samp_mean. I've got 50 sample means, and I got 50 sample standard deviations. And then what we're going to do is we're going to create the upper and lower bounds of our confidence interval. Okay, and so here I'm going to use t star rather than 1.96, but if you want to use 1.96, that's fine. Okay. And basically, so I've got 50 values for sample mean, I've got 50 values for the sample standard deviation, and it says, take the sample mean, subtract t star times the standard deviation over the square root of n. Take the sample mean, add t star times the standard deviation over the square root of n. So this is our upper and lower bounds of the confidence interval. And so now I've got 50 lower bounds and I have 50 upper bounds. Okay, and I can create a graph. And there's a nice function called plot CI, which then takes all of those lower and upper bounds and produces a whole bunch of confidence intervals on a nice little graph here. Okay, and so if we ask for the mean of the population, that's the mean of all 2,930 numbers, and we can plot that. And so in this case, if I zoom here, I did 50 confidence intervals, and actually all 50 of my confidence intervals managed to capture the true value of the population. So the population mean is right around 1,500, 1499.6904. The first, every single line here represents a confidence interval. This dot right here represents the mean of the confidence interval. So, I'm sorry, the mean of our sample. This is a sample of 60 numbers. This is the mean of that sample, and we created an upper and lower bound. And so here we have the upper and lower bound, and so the true mean of the population is contained within this confidence interval. This confidence interval over here, this sample, had a much lower sample mean, but when we created the bounds of the confidence interval, this one over here, it still managed to capture the true mean of the population. Let me try this again, just for another 50. Okay, so here, over here, just because of the random sampling process, I happened to get a sample that had a mean that was much smaller than we might have anticipated. Okay, so if you remember the invisible dog, or I'm sorry, the invisible owner and the dog, this would be one of those times where the dog happened to be more than 2 standard errors or 2 yards away from the owner. This is just one of those times when a random sample happened to be this far away from the population mean. Most of the time they're not. Sometimes it's far away, but just barely within there, and sometimes the sample mean is right next to the population mean. When you take a random sample, you have no idea which one you have. Okay, you're just hoping that because of the nature of the random sampling process, probability kind of favors you in that your confidence interval will 95% of the time capture the population mean, but you never know if it actually did or didn't. Okay, and so so the lab has you use R, the tool, to kind of explore the nature of confidence intervals, and you've got a few questions to answer. Right. Are there any questions? Okay, so if you're struggling with this, don't hesitate to email me. Again, if you're copying and pasting your text and you're running into problems, I then strongly encourage you to, instead of copying and pasting, just try retyping the code by hand, and a lot of times that might solve some of your problems. Okay, just make sure everything is exactly as it should appear. Okay.
Is the final exam